Thanks for coming back after lunch. It's rather strange to be looking way up there. Okay, so this afternoon I want to talk to you a little bit about scalability, but first let me just give you a little more detail. Who is this guy? Did that work? Yes, good, okay. So I'm Michael Nash, as Alex said. I'm Director of Capabilities for Lightbend. I've been working with Scala and Akka for, actually it's more like 8 years, 8.5 years now. Need to update my slides. And I've been a software developer for a very long time. And what I've found over the years is that there are a few things that stick in my mind in terms of patterns that I've seen when I look at highly scalable systems. And I'd like to try to share some of that with you this afternoon. So we're going to start off by talking about scalability. What do I mean when I say scalability? What does it mean? How does it differ from performance, and how does it relate to performance? And what characteristics do we typically see in a scalable architecture? So not necessarily so much about an implementation, but at the architectural level, because it is very difficult to correct a bad architecture with a good implementation. And we'll see that in more detail as we go further. And what do I mean by perfect scalability, and how would I achieve it? How would I head in that direction? So let's start with a definition. Scalability is not the same thing as performance, although the two are related. In some places they're actually contradictory. If you increase performance, let me be more specific, if you increase performance, that means I can run the same load in a smaller period of time. I can run faster. I can handle the same number of requests in a shorter period of time, for example. That's almost the same way that's almost another way of saying the same thing. Adding hardware to a system that is going up in performance will increase the speed of handling requests. Increasing scalability, on the other hand, is a little different. To increase scalability means I can now handle more load without failure. Not necessarily at the same speed or at a faster speed, but without failure. I can handle more requests in the same amount of time or a comparable amount of time, and adding hardware increases my ability to handle more requests, not to respond to the same number of requests in a shorter period of time. This actually makes more sense when you see it graphically, I think. So let's say we have the world's simplest performance graph, or response time graph. So response time is increasing as number of requests is increasing. Simple enough, right? Then if we were to increase performance, we would get a graph that looks like this. All we're doing is moving the whole line down vertically. So we're saying, I've increased performance, therefore every request I'm responding to in a bit less time, or a lot less time if I increase performance a great deal. It doesn't necessarily affect the shape of the curve, however. Like I said, they're interrelated, so often what happens is when you change performance, you do in fact change scalability to some degree. But let's say we could affect performance without affecting scalability, we would get this effect. On the other hand, if I were to increase scalability without changing performance at all, I wouldn't actually, again, change the shape of the curve. What I would do is move the curve to the right. In other words, I can now support a larger amount of load, a larger volume of requests, without failure, and failure being defined in some cases as going way off the end of that hockey stick curve, e.g. your response times get ridiculous. We can handle more requests, not necessarily handle the same number of requests faster. Often, when we increase scalability, we may in fact decrease performance slightly. So, but the two are coupled, and we'll explore that in a lot more detail. So, okay, perfect scalability. What does that mean? What would perfection look like in scalability? I know very little about perfection other than in scalability, as anyone who knows me can tell you. If you add more resources, you handle a higher load. Okay, that's scalability. What's perfect scalability? Perfect scalability would be there is a linear relationship between those two things. In other words, if I add, let's say I can handle 1,000 requests without any problems and in a reasonable response time. I can do that on one node. If I add 2 nodes and I can handle 2,000 requests, exactly, in about the same amount of time, then I have achieved near linear scalability. That's perfect scalability, e.g. that there is a direct relationship between adding resources and adding my ability to handle load. Many systems will look perfectly scalable at the low end of the graph. The time when the picture starts to get interesting is, of course, at the high end of the graph where you discover that it's not necessarily a perfectly scalable curve. So for example, on our the world's simplest performance chart, what would perfect scalability look like? Perfect scalability would mean that there is a cap and then a flattening out of this line. So in other words, at some point here, we're going to have to add more resources, right, which isn't shown on this graph, but we are able to continually increase load without having a problem or without unacceptable levels of response time. That's perfect scalability. So what would a perfectly scalable system actually look like? It's an example of one. Well, let's go sufficiently simple that we can actually prove that something is highly scalable. We add 2 integers. We write a service that can add 2 integers sent over, let's say, an HTTP API. The API is not that critical, but let's assume. The 2 numbers are passed as parameters on a URL. The result is the response. Seems like it should scale pretty well, right? Now, I don't know if anybody's actually put this into production, but we'll get a little more complicated later. So why does it scale, is what we have to start asking ourselves. Yeah, that system's incredibly scalable. What about it means that it's scalable? Is it just its simplicity? Not really. It's other things. For example, there is no state. When I said add 2 integers, that's it. I add the 2 integers, I give you the answer. I don't hold on to the answer, I don't accumulate the answer, I don't do anything else. There's no state involved. So I've got a purely stateless service. Of course, it's easier to scale that. We share nothing. The answer from any one set of combining 2 integers is unaffected by some other computation of some other 2 integers that somebody else has set. So there's no communication between instances of this service. So in other words, all of the communications are independent. That means it'll scale very well. And what's interesting is to start to extract some principles from this, as you'll see later on. It's interesting, though, that even if you build a system this simple, it's actually got a flaw. It's actually not perfectly scalable. It looks pretty good for the first long stretch of that graph. But then, much as our unfortunate rocket friend here, something goes a little wrong way down the line. Why would that be? Where would we see a system like this fail? Well, let's say for the sake of argument that we actually built a system like this and we were doing it via HTTP. Well, at some point, there's got to be a front-end HTTP server that is routing requests to our various services, a load balancer, a router, something like that in the network. If there's only one of those, then at some point that node, that part of the equation, that part of the overall system is going to start to experience very high load. There's a single point of contention. A very scalable single point of contention if we have a really good router, but there is a point on the curve where it's going to start to increase. What that means is that there is actually a little bit of sharing going on in our system. So, how would we fix it? Well, if we actually needed to build a system like this, again, haven't really put one of these in production, but the idea would be, okay, what if we made our client smart enough to select from a series of different URLs such that we don't have them all on the same namespace and therefore not all on the same router? And yes, that really is a rocket with duct tape on it, and that does look like a gas station in the background. Ship it. What could go wrong, right? So, yes, much like our service. The idea here, what did we just change? If I said, all right, let's make a smart client to this thing, or make a little JavaScript that says, I'm just going to randomly pick one of those names to send my request to. And suddenly we discover that our curve has been extended a little further. We're a little closer to perfect scalability. What did we just change? We shared less. Honestly, there's less sharing in our system is the one attribute we changed. This is what I mean by starting to sort of squeeze these examples and say, what are the principles here? What are the things that we can actually determine are interesting to the effect on scalability on our systems that are coming from our design? So, unlike in life, sharing less actually gets us closer and closer to perfection. This is actually a little bit related in some ways to Amdahl's law. Amdahl's law was really intended for single processor systems, but if you take the percentage of your system that can be parallelized without interference with any other part of your system, and the amount of time your system takes to respond to a request, then that percentage plus the amount of your time, the amount of your system that has to be sequential when responding to a request. The two together equaling 100% of your system's execution time. 100 minus that percent that could be parallelized is in fact your upper limit of scalability. In other words, how many pieces of your system could be parallelized is really what that's saying, very simply. Gunther's law takes this a little bit further. Last formula, I promise. I remember, I think it was Stephen Hawking who said the number of formulas in your presentation divides your number of listeners by 2 every time, so there's 2 of them, so all of you have left? Anyway, see, the formulas don't ever work. The bottom line is, Gunther's law takes into effect the coherency delay. In other words, again, synchronization time in its true concurrent parallel system where there needs to be some coherency, some synchronization on a piece of data. And the higher that amount of time is, the less scalable that system is. In other words, the more coherency your system requires, the less its upper bound of scalability is really what that law is saying. E.g., share less, and you'll actually have a more scalable system. So let's say we share as little as we can and we do our best. What typically happens, and the portion of the system that we're talking about where we get away from perfect scalability, I like to call the wall. Basically, it's the point in your system's increasing scalability where adding more resources does not give you a linear, or at some point, any increase in overall ability to handle load. In other words, it doesn't matter if you throw more servers at it, you're not getting any better. You're not actually handling any higher load at all. That is the point on that graph of the hockey stick where it's starting to approach vertical, where it doesn't matter if you add additional resources, there's something about the design of your system, something about some attribute we've neglected, which is suddenly causing our system not to be scalable. And over the years, I've seen this again and again in a million different ways, and there were always common characteristics to the thing that was causing the scalability to not happen. So we haven't failed to find scalability, but we have in fact discovered 10,000 ways that won't work. And I think as an industry, we've now gone well beyond the 10,000 ways that won't work. So how would we go about, what would we see in a system that avoided some of these traps? So how do we avoid the wall? How do we get to the point where that hockey stick curve, okay, maybe there's some degradation of the additional amount of load we can handle with adding additional nodes, but that it never starts to go vertical until maybe way out there, if at all. How do we avoid that wall altogether? We would do that basically by avoiding what I call the enemies of scalability. So in other words, the things that trap a system somewhere further down that graph. And those are, and I'll talk about these in a little more detail, things like contention, shared state, which is not the same as contention necessarily, although it can be depending how you go about it, sharing at all, which cannot necessarily be sharing state but other information, ordering in sequence, which is an odd one that we see a lot and is actually a huge problem, communication, which is odd to say that that's a problem in a system, because if we're talking about modern microservices and reactive architectures, obviously our services communicate. And of course, failure, which gets more and more relevant the larger and larger your system is, because the probability of any one piece failing is going up. Let's talk about some of these in detail. So, avoiding contention. Contention comes from parallelism or distribution, distribution being a special case of parallelism where the parallel pieces are on multiple machines, where there is shared state. So in other words, some piece of information needs to be common to more than one element of this distributed system. Not having shared resources of any kind reduces this. So the absolutely most egregious example of this would be a shared database, for example. Then you've obviously got a single point of contention. If there are writes happening to that single point of contention, your scalability will be severely limited. We'll talk a little bit about how to get around some of these issues later, but first I want to define what the enemies of scalability are. So how would you go about avoiding sharing? Well, get each dog their own stick is the short answer. I always like to use that analogy. In other words, have more than one instance of the state and have that state be private to the individual component of your system that requires it. Now, that still requires communication, I hear you thinking, and that's true, but there are advantages to it. So there's nothing wrong with state. I'm not saying that you need to build all of your services stateless. Some people got that from my example. Okay, we can only add integers if we want scalability. Well, yes, but we live in the real world. So state is fine. Nothing wrong with state. Your service can have all the state it needs. However, that state must be private to each individual component of your system. That's a little harder. And it actually is a design challenge. It's not something you can bolt on after the fact. So common ways of solving that problem are that events in your system, e.g. requests to that where something has happened in the past, an event something happened in the past, command something that's happening in the future, can broadcast deltas to that state to other services or other elements of your system. Using the term services, not necessarily, could just be other components of your system. Private state inside an element can then be updated from these deltas after the fact. What I'm talking about is essentially event sourcing and eventual consistency. But that's why it helps scalability. Now, this is an odd one. We talked about communication being an enemy of scalability, and yet all systems need to communicate to some degree. I think the change in thinking for a highly scalable system is to consider communication a cost, and to look at it that way. Every time I want a service to communicate anywhere else in my system, that costs. How much it costs depends, of course, on the volume of communication, how frequently I'm going to do it, how slow is the thing I'm communicating with, can I do it synchronously, can I do it asynchronously. However, it's still a cost. It's not free. So by taking into account that, even on a local system, so for example, if you have a parallelized system on a single node, and you have those elements communicating, there is still a cost. Sometimes a very substantial one. Bizarrely, we've had systems where the entire reason they couldn't scale any further was the cost of serialization of messages between nodes. We improved the serialization, suddenly the whole system scaled 3 times faster than we thought it should. So think of communications as a cost and take it into account. For example, Akka clusters crossing data center boundaries might be too high a cost. You might not want to do that. For a lot of detail reasons that we could talk about offline if you're interested. Another very common one is that systems will frequently be designed with ordering as a requirement. Ordering, that is, the sequence of elements to take place as a requirement where not necessary. Now, in some situations, I understand, ordering is required, but usually it isn't, and usually it isn't global ordering. That would actually be the worst kind of flaw in terms of a scalability enemy, is to assume that global ordering is in fact required. Because when you think about it, ordering requires some form of shared state. Somehow I have to communicate who's first, who's next. Can't necessarily do that with clocks, isn't necessarily reliable. There's a lot of different ways to go about it, but they're all compromises. If I said instead, it's actually okay to have all of these operations done in any order that's necessary, I remove a constraint in my design that is very difficult to program around afterwards. Like I said, implementation is far too late to think about scalability. You can't implement out a design flaw. Avoiding system failure while effectively embracing element failure. So a distributed system, by its nature, is much more likely to have something fail. It is hopefully, if you've designed it correctly, much less likely to suffer a systems failure as a result of that individual failure. But just because you've got more working parts and more nodes and more network and more things, the chance of something going wrong is actually higher than if you had a monolithic system. The less we share, the less likely is a systems failure. Whereas if we shared everything, then any one element of our system failing would in fact bring the whole system down. Right? Just like a chain, having a link break. So that's one way to think about tolerating failure, is to think about reducing the sharing. Avoiding linear time. Linear time is in essence a form of sequential ordering. So we're saying if things have to happen in a specific sequence, then we're insisting that there is ordering based on those transactions or operations in our system. Using things like, for example, finite state machines and single-use actors can avoid some of that. Communications must also very critically avoid linear time, e.g. all communications, especially between services, but between a service and any external system, should be asynchronous and non-blocking. Yes, you still have to design that in, and yes, it is still harder than doing a sequential system. Nobody ever said distributed systems and highly scalable systems are easy. These are some of the constraints we would have to operate within in order to achieve high scale. So what does that do to our overall systems design? What constraints are we now operating within? Well, basically, we've talked about a series of principles, a series of not individual steps in building your architecture, but things to keep in mind as you build each piece of your architecture. Building services and systems designed to adhere to these principles will make them easier to scale than systems that don't, is my whole contention. That it is easier to think about these things at the point where you're building not only a design, but also an architecture, related but not quite the same. And tuning cannot fix a bad design. If you have a bad design, implementation can't fix it, tuning definitely can't fix it. Turning the knobs at the end will not help, particularly. Not at the level we're talking about in terms of making a quantum leap of scalability. So a scalable architecture, you've probably heard some of these tones before. No single points of contention. Nothing's shared, or as little shared as possible. And the way you share matters. The way that we talked about sharing is much better than what is commonly done. No state. So no state at all would be great if you're only adding integers. If you do have state, keeping that state private is critical. And no synchronous persistence. We'll talk a little bit more about persistence in a few minutes. Scalable architectures not only scale up, but one of the requirements of modern architectures is elasticity, not just scalability. E.g., the ability to not only scale up, but also scale down. It's critical to think about what happens with your system when I want to actually reduce the load it's running on, because the graph runs in both directions, not just in the upward direction. And the upward direction is all very well and good for times of extremely high load, but it also represents times of extremely high cost, in the sense that you need an awful lot of hardware to do that. Now, one of the great advantages of putting systems out in the cloud is that I can only pay for the hardware resources I require. Well, what happens when I don't require them? Can I scale my system back down again? Can I address the low end of that curve? That's as important, in some cases more important, than even addressing the upper end of the curve. So a system has to be designed to scale up and down. So what are some of the characteristics? Let's talk about way up in the hockey stick side of the curve. What are some of the characteristics of an ultra large scale system? So thousands of nodes. We've got customers that have Akka clusters that have 12,000 nodes on them. What does that look like? What are some of the characteristics of that system? How do they succeed? They tend to be not a single system. For one, they tend to be a system of systems. So there are several macro pieces communicating with each other over narrower channels, particularly when they're distributed across multiple data centers. Having a single cluster across multiple data centers is usually not great. They share a lot of the characteristics of organic systems. And there's been several great articles about this. Everything is decentralized. So there is no, for example, Zookeeper is often found to be a bottleneck in a highly scalable system. Because even though it is clustered, it is to some degree that system becomes a single point of contention over time. Everything being decentralized is critical. Handle conflicting requirements. Frequently we will see ultra-large scale systems with more than one version of a service running simultaneously, doing exactly the same operation, and yet surviving that. That's critical, again, if you want to have your system scale not only in the sense of user load, but also in the size and complexity of the system, that it is tolerant of that kind of conflict. Often internally inconsistent. There will actually be 2 customer updated events flying around, and that's okay. The system can continue to operate, for instance. The users affect the overall emergent behavior. In other words, it is very difficult to predict the performance characteristics, the failure characteristics, the scalability of an ultra-large scale system ahead of time. Having actual live users on it will actually affect it in ways that are very, very difficult to predict or to simulate. That's one of the reasons monitoring is so critical, and we'll talk about that a little bit more too. And failure is actually the norm, which is odd. On ultra-large scale systems, we found that at any given time, there are definitely some pieces of the system that are offline. So if you build your system from the start to say, that's okay, we gracefully degrade, maybe that particular kind of operation isn't available at the moment, but overall the system survives. It's like, when you cut a fingernail off your body, you don't die. The same has to be true of ultra-large scale systems. So spike load, this is almost the opposite of the scaling down slide. The rapid increase in load is actually characteristic. We have a couple of clients where this is their characteristic. This is their defining way their system operates. They have a certain event that happens at a certain time of day, and they have a tremendous issue with spike load. Sometimes you're going to get more users than you're expecting. This is the good news, it's also the bad news. Failing by success is one of the most popular things in systems, where you go, great, look at all the users. Oh no, great, look at all the users, right? And then suddenly your system starts to suffer. Even a perfectly scalable system, a system with perfect scalability that we're describing, can be taken down by spike load. That's because you cannot necessarily instantaneously add additional resources to handle that load. You've got to be predictive and say, all right, I have to actually have resources online before the load, or start adding them more quickly based on the rate of increase in the load. You can't linearly respond to rapidly changing load. So again, having a system that is capable of degrading gracefully, where your performance is going down, but you're still handling all requests, is far superior than having a system that can respond 5 milliseconds faster, but as soon as I go over a certain line, it's going to blow up on me. One of the ways spiked load is handled that we've seen over and over again as a pattern, just incidentally coming one level down into design from architecture, is a technique called command sourcing. So I said earlier that there are messages in a message-driven system, in a reactive system. Those are differentiated into commands, a request for something to happen in the future, which could fail, and an event, which is actually a notification about something that has already happened. An event can't fail, it's done, right? Customer has been added. We're not saying, please add a customer. We're saying the customer has in fact been added. That's something that's happened in the past. If we persist our commands initially on entry into the system, we often find we're in a situation where we can handle the commands asynchronously and therefore handle spike load better. Because frequently persisting something into a queue, let's say Kafka, we often see Kafka in this role, provides what amounts to a shock absorber on your system. The ability to have that load suddenly increase simply means Kafka gets busier for a while. The actual rate at which you're handling those requests can remain constant on the back end. As long as you can store them and don't lose them, nothing goes wrong with your overall system, except of course your response times go up temporarily. Then, going in the opposite direction, we talked a little bit about graceful degradation. I love this quote, you know, an elevator can never break, it just becomes stairs. So, a situation where you have a reduction in system capacity by taking a subsystem offline or having some kind of overload, simply reducing the number of capabilities you have in your system is far superior than having one critical service in your system that everything else depends on, say the login service, that when it goes offline, everybody dies. That's a flaw at the design level, not at the architecture level, at the architectural design level, but not at the implementation level. Think about graceful degradation. Because again, highly scalable systems, there's always going to be some piece of it that's broken. Of course, the buzzword of the day is microservices, one of these words that's been overused to the point where I'm not sure there's any juice left in it. What microservices buy you at a cost is usually worth it from the scalability point of view. Both scalability, and we're talking here about system scalability, the ability to handle load. Some of the other things you get with microservices are the ability to scale your team, to scale the ability to build services. And that's a whole different animal. So often that alone is actually worth the transition and the cost of microservices. But they're worth it if they provide some of these key advantages. Otherwise, you've just got a monolith sliced up. If you've got async communications with other services, so in other words, you're not limited to your slowest service, your services are isolated, so failure in one does not bring down the ability to handle load, and you have services that handle a single responsibility. That's very much related to the previous statement, such that a function could be tuned independently. That's also critical. So let's say, for the sake of argument, for whatever reason, logins are actually a very expensive thing on your system. Great, fire up 20 more instances of the login service. Can't do that if you have a monolith and all of the services come together. All you can do is fire up 20 more instances of everything. That's very different. You can't shape your load, you can't shape your capability to match your load. So microservices are critical in the scalability area. And also microservices must own their own data, which is not shared with other services. Otherwise what you actually have is a monolith in your database and bits hanging on the outside that you're calling microservices. That's a design that does not scale. Simplicity is also critical, and sometimes you can buy some simplicity with microservices in the individual services, even though your overall system doesn't get any simpler. So if your system's architecture diagram is starting to look like this, you're probably in trouble. All things being equal, easy is better than hard. That was a sort of a truism that somebody said to me once, and I'm, yeah, okay, I see that. Simple patterns, and the kinds of patterns that we've been discussing, consistently applied across all of your different services, obviously scale better. Again, some of these things sound pretty obvious until you actually look at them against how your systems design might be evolving now. A critical thing, and Jonas from our company gives a great talk about this, is to avoid the concept of a global now. There is, from a physics point of view, no such thing, as he goes into in quite some detail. But the worst kind of coordination and the worst kind of sharing is temporal sharing, time sharing. Another one of my favorite quotes, a man with two watches never knows exactly what time it is. A man with two nodes, a system with two nodes never knows what time it is either. It can get pretty close, but arbitrarily close, theoretically, but it can never actually converge. So clock time cannot be used for ordering, generally. Things like vector clocks and fancy things like that allow you to work around that problem. Better, I would propose, is to have a design that allows you to not have the problem. and have a design that does not require ordering temporal or otherwise, if at all possible. Causal ordering is superior than temporal ordering, but still causes some constraints. I talked a little bit about persistence previously. Obviously, any non-trivial system likely has to persist something at some point in its life cycle. Persistence doesn't necessarily have to be the worst bottleneck. E.g., if the way you measure the scalability of your system is by measuring the scalability of your database, then I would propose that there are ways you can improve your design. The file system, oddly, is often the fastest choice. For example, Kafka, by default, actually streams everything into the file system. And it seems sort of old-fashioned, but it's actually one of the fastest choices frequently, particularly with modern file systems. Streaming is your friend. Persist where you need to recover. This is a big one. This is a mantra I keep repeating at customer sites. Persistence means that I can pick my system up from that point and repeat any of the transient operations it was operating on from that point. So therefore, I only need to persist where I need to recover. I don't need to persist all of the individual stages in between if it's cheap, easy, and idempotent to be able to recover them. It's actually far better to just do them again. So idempotency, of course, is a big deal. And watch out for secondary indices and clustered or sharded systems. They are also performance killers, of course. We frequently see Cassandra, Postgres, HDFS in the space of persistence and highly scalable systems. Now, I mentioned this briefly before, but this is again a mantra I repeat a lot at customers, is the idea of keeping your hands out of OPD, other people's databases, I call it. In other words, never snap on the big blue glove and reach into somebody else's database to grab data. That should be as impolite as it sounds. The worst thing to share is a database or any form of storage. So what you're really doing is saying I'm making the slowest part of my system up to 1,000 times slower than inter-process communication, the thing that I'll communicate with. That's generally a bad idea from a scalability point of view. It's also a bad idea from a design point of view. Even if you find that this requires a certain amount of denormalization and duplication of data. Normalization is not a friend of scalability. They're actually competitors, if you like, enemies to each other. So services have to keep their mitts out of other people's databases. CRDTs and event sourcing are one of the ways we see this solved. Now CRDTs, when you think about it, are actually a specialized instance of event sourcing that simply converge on an end state. Distributed transactions. How do I do a distributed transaction in an Akka cluster? Was a question we had recently. The correct answer is please, please don't. The distributed transaction is an attempt to do exactly what we were talking about in terms of stop the world, make a change to the world, carry on with the world. It's not the way physics works, and it shouldn't be the way your distributed system works. It's actually one of the hardest things to try to scale around if there are situations in your system that are even beginning to resemble distributed transactions. If you find yourself going, I kind of need a distributed transaction to do this, back up and have another look at your design. There's almost always another way. There are techniques that can actually lead you design-wise to a way to avoid a distributed transaction. Now, one of the things that you will want to do to avoid distributed transactions is to have most of the operations in your systems idempotent. In other words, the idea of being able to repeat yourself, is actually critical to be able to allow for failure in a single step. Therefore, command sourcing that we talked about earlier can simply repeat that step without anything bad going on in your system. That is a hugely valuable trait. When you're designing scalable services, consistency is critical. Consistency is often driven by starting with some design principles. I would highly recommend having a read about domain-driven design and distributed domain-driven design, which is a related technique. And it is not directly related to scalability in the sense that you can build a system that's highly scalable that has no coherent design from a DDD point of view at all, no ubiquitous language, none of those. However, if you pick a set of principles for your design, it will allow you to scale from the development point of view much more readily because all of your services will have a familiar pattern. And it will be much easier for you to make sure that you're actually adhering to some of the principles, which are by and large about avoiding things as opposed to doing things. But it will make it easier for you to do that if you're following a certain set of design principles. And DDD is one of the good ones. Now, of course, balancing scalability. This talk is all about scalability, so I'm emphasizing the ability of your system to scale. Systems that scale ridiculously but only add 2 integers are not all that useful. Obviously, you have other things that you must balance with your concern for scalability. Features, velocity, simplicity, cost are all considerations that you have to balance against scalability. But there should always be a consideration. If you say, okay, we're taking this design decision in our system, and we understand the cost that that will have in our ultimate scalability, and that's okay, great, good decision. If you're taking a design decision and you go, didn't really think about it in terms of scalability, very hard to go back and fix after the fact. So that's what I would recommend. Okay, trust but verify, yes. Distributed and parallel systems are by definition non-deterministic. In other words, you don't actually know in what order things are going to happen or how your system's going to behave under load until you measure it. What that means is that being able to simulate and being able to monitor that simulated system and monitor in production are critical. Load tests are a necessity, not a nice to have. If you're going to build a system whose goal is high scalability, the first thing you write is your load test. To say, okay, here's the test I must pass in order to say I'm actually meeting the SLA that's required. No other tests matter. Now I have my first feature. Then if I didn't break that test, I can add a second feature and keep going. That's how a highly scalable system is built, from the ground up in pieces like that. The log is not enough, to quote James Bond. The idea being you cannot in fact determine or diagnose a problem in a highly scalable system from just a log. And if any of you have ever tried, you would probably agree with that. I'm sure people that have tried this and they're like, there's logs all over the place, great, we're consolidating the log, that's fine, that's important, but it's not enough. You also need monitoring to be able to see in real time what the characteristics of your system are as it performs. Be careful how you monitor though. We've actually seen customers that have monitored their systems to death by having literally enough network traffic on monitoring that it started to affect the overall scalability of their system. Nobody ever said this stuff was easy. DevOps matters a lot, obviously. When you're talking about a highly scalable system, there's probably going to be at least dozens, if not hundreds, if not thousands of nodes involved. Being able to do something so simple as a rolling upgrade is critical, in the sense that if you can't do a rolling upgrade, well, you certainly can't have a piece of the system go offline. So therefore, you wouldn't be able to recover from a single node failure in any case. So it's not just technology or tools, it's culture. And you'll hear all sorts of other great talks that talk about that. We often see things like our own Conductor product, Mesos, DCOS, Docker, Jenkins are all involved in the DevOps process. If you start with a DevOps mindset, you'll have the better time building a highly scalable system. Okay, so perfect scalability is in fact achievable, or at least as close as you need to come with the appropriate balance of constraints in your system, but not with every design. It is not possible to scale some designs. And this is the unfortunate news that every now and then we have to tell a customer is that yes, that's a great idea, but no, you're not going to handle 100,000 users on it, just not going to happen. Let's go back to the whiteboard. So therefore, designing with scalability in mind reduces the cost of you changing your mind later. It's much easier to say, take a scalable design and go, we just don't need to throw that many resources at it, than later to go, uh-oh, we're being killed by our success because we have 5,000 new users a day coming on and here comes the wall. Nobody ever wants to see the wall at that point of success because it's a very, very bad time to go back and start redesigning. So one of the main principles I can leave you with is to avoid those enemies of scalability in your design as much as possible within the constraints of reasonable. Find patterns of design that don't use those enemies. Things like event sourcing, CQRS, these things are actually a lot easier with modern tools than they used to be years ago. Monitor. Monitoring is critical, and adjust your running system to be able to correspond to what you're seeing in your monitoring, and be able to embrace and handle failure. So things like individual nodes being able to go offline safely. Okay, I've berated you enough about scalability. Anyone have that expression and have questions to ask? Thank you.